My friends, today is lecture 2, is that correct? So today we're going to be doing hydrostatics. Before we do fluid mechanics, which is the motion physics of fluids, today we're going to be doing hydrostatics, which means fluids that are still. Okay? So this is very important because we're going to see this a lot. Okay? If there's one lecture that I'm going to be focusing on the most on, it'll be this lecture. So let's see. So today is going to be hydrostatics. So hydrostatics means that, well, it's statics for fluids. Newton's second law, you can set it equal to 0. So that's statics. So if you've already taken a statics class, that's great. So y'all mechanical engineers, you're already on top of your stuff. I almost said something else. But for the chemical engineers, we got to catch ourselves up. But that's okay, because we don't go too in-depth with the statics. But statics means, I want you to write this down, memorize this, or understand this. Alright, statics means that we're going to add summation of all forces. Newton's second law is going to be equal to 0. Okay, that's crash course of statics. I've never taken statics, but that's all I know about statics. He said all the forces equal to 0 because why? Because it's in equilibrium. Okay, so using this notion, let's see if I can derive this from scratch in one take. Let's see. So my friend likes to call this the fluids box or the transport box. It comes up a lot for some reason. So I'm gonna draw this. I'll draw this over here. Okay. So this box. Okay. Well, let me draw another picture. I didn't know what to get you for Christmas this year, so I gave you this box. Or was it birthday?
That's what I got you.
All right. So let's say I'm gonna draw a cup of water, and you're not an engineering lecturer if you don't say something along the lines of like, I'm not an artist, I'm an engineer. So I'm not an artist, I'm an engineer. So if we zoom in on a little box right here, okay? Imagine a fluid box, okay? This is where it gets a little theoretical because we're imagining a fluid box, okay? So because of the pressure forces, there's like some force up there, some force down there. What kind of force? Buoyancy force. Remember buoyancy force in physics? So this box is going to represent a box of fluid inside the cup of water. And so namely, well, if we draw this in 3D, right? Change this angle like that, something like that. Alright. Alright, so this is our 3D box, and what do you do when you draw 3D stuff? You gotta draw your axes. For my axes, I'm gonna use horizontal for X, the inside of the board is gonna be Y, and the vertical is going to be Z, or Z. Z. Alright, so that means this is going to be x equals 0. So this point is going to be x equals 0 going horizontally across. It's going to be delta x. X equals delta x. Alright, can y'all see that? Alright, so this term is going to be delta x. Similarly, this will be y equals 0, and this will be y equals delta y. So this length will be delta y, okay? And up here, you already guessed it, it's going to be delta z. So notice how this is z equals 0, and this is z equals delta z. Alright, so summation of all forces equals 0. So remember, force is a vector. For vectors, they have components. So let's do it one at a time. Pick and choose. I'm going to just choose x, because I'm setting up for something. So summation of all forces equal to 0. I'm going to say 0 is equal to, in the x direction, well, what are the forces we got here? So there's some pressure, right? Imagine in the block, there's some pressure pushing the fluid that way, there's some pressure pushing the fluid that way, which makes sense because it's in equilibrium, okay? So there's a force in the x direction, there's another force in the x direction, okay? But notice how this is going to be f of x equals 0. So I'm going to write, so this bar just means that it's going to be x equals 0. Can you all see that? Yeah, if I can see it, you can see it, hopefully. It's not good logic, but I know. And then this is going to be, extend this, all right? Can you please do me the favor and imagine that I'm extending this? It's going to be f at x plus delta x, right? X plus delta x. Okay, so at x equals 0 and x equals x plus delta x. Okay, so this is a general form, so just kind of bear with me. So Let me move this 0 over. Okay, makes sense? So we got one force coming this way. It's going to be positive, right? Because look at the axis. And one force coming the other way. It's going to be negative. So it's going to be F at x equals 0 minus F at x equals x plus delta x, right? X plus delta x. All right, so we're done, right? So that's our equation. Yay! The forces are the same, but check this out. Because pressure equals force over area, force equals pressure times area. All right, so we can plug that in. So it's gonna be the pressure times the pressure at x equals 0 times the area minus the pressure at x plus delta x times that same area. And what is this area? It is this cross-sectional area, if you can imagine that. Okay, can you imagine that I'm filling in this cross-sectional area? Okay, what is the area of that going to be? It's going to be delta y times delta z. So we can plug this in. Pressure is going to be delta y times delta z minus x plus delta x times delta y times delta z. Great, hope you can see that. And look, you can cancel these terms. I don't even have to move it over. You can see that the pressures and the forces are the same. So the pressure on the left at x equals 0 is equal to the pressure on the right at x plus delta x. Well, you're probably thinking, well, that's kind of pointless, because it kind of was, but it kind of wasn't, because we're really proving that the fluid is in equilibrium. It's hydrostatic. It's hey, maybe that's why they call it hydrostatic. Sometimes even I wonder what I'm thinking. So I want you to do it again for the y direction. Okay, so pause the video, do it again for the y direction. And the z direction. Did you get the same thing? For the y, it should be the same. But for the z, maybe not so. Because, well, what are the forces in the z direction? So let me get rid of this. Let me redraw the box again, because this is where it gets a little bit tricky. So the box is going to be like SpongeBob. Okay. Okay. And so this is going to be our delta x, delta y, delta z. Let me move the delta x. Remember that the horizontal is delta x. Well, there's some force pushing down. So that's a force pushing down right there. There's this force. Okay. There's another force pushing up. And there's gravity. Force of gravity. So this force is going to be at z equals 0. That's right. And this force is going to be at z equals delta z. Delta z. So summation of forces at m equals 0. So this is 0 in the z direction now. Z is that equals, well, positive is up. So I'm going to say this one, F at z equals 0 minus z equals delta z minus gravity. Plug everything in. So we know pressure equals force over area, F equals ma or mg because of gravity. So we have 0 equals, so this area we're looking at is going to be the shaded region, delta y, delta z. Okay? So a little trick that you can do for picking the area, when we're looking in the z direction, when we looked in the x direction, the area was delta y times delta z. If you did it for the y direction, you'll notice that the area was delta x times delta z. And now for the z direction, it's going to be this area, which is delta x times delta y. So it's whatever you're not looking at. But don't memorize the trick. I want you to visualize it in your head. So pressure, force equals pressure times area. So it's going to be pressure in the z equals 0 direction times that area, okay, minus the pressure the z equals delta z direction, minus force of gravity, mg. Okay? And forgot to multiply by area here. It's the same area. And I'm going to write equals pressure, again, at z equals 0, times the area, which you said was going to be delta x, delta y, delta x times delta y, minus the pressure at z equals delta z. Little notation trick, you're going to write delta, and then parentheses, you're going to write x, y, so that just means delta x, delta y. Might use that, it's a little convenient, minus the gravity terms. Great, okay, alright. So what I'm going to do is, something's a little funky here. So what I should do is, I'm going to start by dividing. Well, there's many things we can do here. Just trying to see what's the most intuitive. What are y'all thinking? What are y'all thinking? Well, notice how we have mass over here, and this is why the dimensional analysis is important, because if you know mass, you have some length terms. What has mass and length? Density? So density equals mass over volume. So now we want to divide everything by the volume. So let's just do that. Divide everything by the volume. So I'm going to say 1 over delta x, y, z, because that is the volume. So 0 divided by anything is still going to be 0, but I have to divide this term as well. Do you see what I'm doing? I'm kind of skipping a little bit of some logic, but it's going to be p z equals 0. Delta x, delta y divided by delta x, delta y, delta z is going to be delta z. P at z equals delta z. Delta x, delta y divided by delta x, delta y, delta z is also going to be delta z. Alright. Minus mg divided by delta x, y, z. Oh, interesting. So now I can factor out this guy. So I'm going to say p z equals 0 minus p at z equals delta z divided by delta z minus mg over, hey, wait a second, delta x, delta y, delta z. Didn't we talk about in the last video? That's actually what? Volume. Hey, wait a second, mass over volume. You're getting this better than I am. It's going to be rho g. Alright, alright. That's looking like something pretty interesting. Well, remember, final minus initial. This is actually down minus up. So, excuse me, this is up minus down. So why don't we just rearrange this so that it's moving? Let's move this to the other side. So I'm going to say p. Now I'm gonna move this guy over. So now this is going to be positive. P at z equals, you can still see that, right? Pz equals delta z minus p at z equals 0 divided by delta z. So let me know when you can't see it, and then I'll just, or you can't let me know. Okay, so I'm just moving this over. This is still negative. And that looks pretty good. That looks pretty good. Just to wrap it all home, what you can do, hey look, this is delta z. If we take the limit, as this guy approaches 0, let's take the limit as delta z approaches 0. Huh. You know, that's pretty familiar. So this is going to be a what? I'm sorry for erasing this, but I'm just too excited about this. Let me rewrite it, okay? Make sure we're on the same page here. P at z equals delta z minus p at z equals 0 divided by delta z. You see what I'm getting at? Negative rho g. And we just said we're taking the limit as this guy approaches 0. Delta z approaches 0. Now that means what? That means we're done because we have a differential. dp dz equals negative rho g. And this, my friends, is called the hydrostatic equation. It's called the hydrostatic equation. Hydrostatic. it makes me hydrostatic that we just solved for this equation by ourselves. That's all for this video. Click over here. This is the playlist. Okay. DPDZ.